also belong to Université Côte d'Azur, which is a new agglomeration of research centers and universities here in the south of France. And here are some pictures trying to attract you towards the resources and nice environment that we have here for research. I want to acknowledge the funding from the university. And please, keep an eye on the PhD opportunities and postdoc opportunities that may arise from our lab. Currently, we do have an open PhD position in computational seismology and geomechanics. It's about how earthquakes trigger submarine landslides. Is something that did a submarine landslide happened in the region several decades ago in the airport, and now we're trying to understand if earthquakes could reactivate this unstable slope, and more generally how dynamic triggering happens for submarine landslides. So this would be a PhD combining computational seismology and geomechanics and seismology observation. All right, so here is an overview. I will give you a general introduction to earthquake dynamics. What is it and why does it matter for you? As far as I understand, many of you are more into earthquake engineering. And then I'll jump into current research topics, so it's more advanced topic, but I'll try to present it in a very intuitive way. And it will be focused on the size and the speed of very large earthquakes. And it will be a combination of seismological observations, theory, and simulations. Here's a movie that shows dynamic rupture simulation. What you see here is a cross-section of the Earth, right? As if we had opened the Earth to see inside a fault what is happening during an earthquake. From the hypocenter, there's a slip that starts to propagate across the fault. That's in the leading edge of that slip area is what we call the rupture front. And this radiates waves, and when we see in map view, for example, here are the ground motions that are produced by the earthquake, and that's our main observation that we have to understand earthquakes, but also what carries the impact, the damaging impact of earthquakes. And as you can see, there's complexity in this wave field because in this simulation there was roughness on the fault plane geometry and also roughness on the crustal structure that produces wave scattering. Here are the basic ingredients of dynamic rupture simulation. Let me put the pointer. We need to assume basically three things. One is the fault geometry, and this is a very basic example of a planar vertical fault. We need to also make some assumptions about the properties of the surrounding medium, and very often it is assumed to be elastic, and we do have some constraints on the elastic properties of the crust that we can use for the simulations. Another important ingredient is, well, the boundary condition that we will apply on the fault, and this is governed by what we call a fault friction law. So here's one example of a fault friction law, which describes how the strength of the fault changes as a slip advances. We also need initial conditions for this, and here's an example of the initial stresses assumed on the fault before this simulation. In terms of equations, we are basically solving the seismic wave equation with a nonlinear boundary condition on the fault given by the friction law. And given the initial conditions, which these initial conditions are designed to operate a little push initially on the fault. So for example, the initial stress here close to what will become the hypocenter is very high, is very red. So that will give it a push, and rupture will then start propagating spontaneously. So once we do that, we end up with results like in the movie I showed before, and here are 4 snapshots of a movie like that. We are looking into the fault plane at 4 different times, and all this process of rupture happens in a few seconds. And the rupture expands over the fault at speeds that are on the order of several kilometers per second. And we are interested in seeing how these patterns develop of rupture fronts progressing on the fault plane, and how this complexity, how complicated patterns start to emerge, how they radiate waves, and how does that have an impact on the ground motions at the surface. These three ingredients here have certain degrees of uncertainties. Fault geometry is something that we can very well constrain at the surface when the fault is not a blind fault. We can, through seismic imaging or by looking at aftershocks or seismicity, we can try to constrain the geometry of a fault at depth. The friction law, well, mostly it comes from what we know about it comes from laboratory experiments, theory also, and some constraints on some of the friction parameters from seismological observations. And the initial conditions are a big unknown. It's very hard to, well, it's impossible to measure the stresses at the resolution that we are seeing in this figure. So most of what we assume here about the stresses is the smooth average values plus some stochastic component. Here's a simulation that shows you, to highlight that we are now in a good position computationally to run these simulations for very large earthquakes that involve complicated systems of multiple fault segments. And this is the earthquake that happened in 2016 in New Zealand, the Kaikoura earthquake, and it broke almost 20 different fault segments. We did this study to come up with friction parameters and initial stresses, that's shown in the left, that could lead to a rupture process that matches the main observations, seismological and geodetic and field observations. So that's a process of tuning these dynamic models to reproduce observations. It's a sort of inverse problem by which we try to learn about earthquake physics and the state of stress in the crust based on these observations. These simulations can produce ground motions also. We can compute seismograms out of those sources. Here on the left, the figure shows the peak horizontal ground velocity. This is for a scenario of a big one earthquake in Southern California. We can look at the seismograms in more detail. And this is something that is useful for the earthquake engineers and for people who are interested in the impact of the earthquake. And so that's a forward problem. We are also interested in the inverse problem, which is to infer what happened on the fault given the observations that we have done at the surface. But coming back to earthquake engineering, there's here are some of the basic steps in seismic hazard assessment to simplify the process, right? We estimate first the probability of occurrence of an earthquake of a certain magnitude. And then for those earthquakes, we estimate the amplitude of the ground motions they could produce. Now, this second step here, which is the ground motion prediction, is usually based on empirical approach, which uses ground motion predictions equations, which are regressions between ground motion parameters, PGA, PGV, and so on the one hand, and on the other hand, source or site parameters, such as the magnitude, the distance to the source, the class of soil, and so on. And these ground motion prediction equations are derived from recorded seismograms, so they are empirical. And this comes with a limitation. It works fine as long as you do have data that samples the areas and situations of interest. But the problem with the available ground motion data is that it has gaps in it, and those gaps turn out to be in places and in situations that matter a lot for applications. For example, there's a scarcity of observations at close distances to sources. So each dot in this plot here on the upper right is a recording available as a function of distance to the source and as a function of the magnitude of the earthquake. It is because of this gap here in the empirical approach that we need to complement it with other approaches. And that's what we call the physics-based approach, is either try to do source and wave propagation simulations that encapsulate and contain our best current knowledge about the rupture process and wave propagation process, and use that with certain confidence to fill this gap here. So that is one of the interests of doing dynamic rupture modeling from the applied side of seismology. Today, we will focus on doing physics-based modeling of two key source parameters. One is the earthquake size, and the other is the earthquake rupture speed. So let me now explain why these two parameters are important, and let me start with size. Here's a map of part of South America, the Pacific coast of South America. And I love to talk about this region because I was born and raised in Peru, and it's an area where very large earthquakes happen. And these figures come from a paper by Juan Carlos Villegas Lanza, and I also like to use his papers in my presentations because he is one of the he was a grad student who was trained thanks to funding by my institution, and after he graduated, he came back to Peru and has now a permanent position in the Peruvian Institute of Geophysics. So he's a good example of a success story of the mission of my institute, to train people from the global south. We're going to focus on Peru, which is, and in particular the coast, so this dashed lined box here. So here we are again, focusing there. Each of these circles, red here, are past earthquakes. And the past earthquakes are also plotted in this other diagram here in the center. They are plotted in the following way. So the horizontal axis is time, and this spans several centuries, almost 5 centuries of record. Of course, the instrumental seismological record only spans about 100 years, and then everything before that is historical records, so the written record, which starts with the arrival of the Spaniards. The Incas and the pre-Columbian cultures did not have writing. Okay, so in this plot here, the vertical bars show the extent of the rupture in each of the earthquakes whose magnitude and date are marked next to it. And you can see that the seismicity, historical seismicity in Peru organizes more or less into 3 big segments that are separated by 2 barriers here. And what makes that separation is that if you focus, for example, in the central segment, there are earthquakes of various sizes, but they never have broken through these barriers here marked in orange. Sometimes there are big earthquakes that span the whole segment. Sometimes the segment breaks in 2 times that are separated by a few years. And we can see similar things in other segments. And this is something that is pretty common in many subduction zones. It's what we call segmentation. So we would like to understand what makes a barrier and how efficient is a barrier. We have not seen them breaking in the past 500 years, but is it possible that it will break in the future? So those are the sorts of questions that are important. And of course, the larger the earthquake and the larger the damage. So that's why it has an important effect on hazard. Here is also some of the observations that can help constrain this question. And this mainly comes from crustal deformation observations based on GPS data, from which one can infer what we call seismic coupling maps, that's shown on the right here, which essentially in this map, the red areas show places on the fault where the sleep deficit is accumulating very fast. So these are the areas that are accumulating most energy, potential elastic energy, and it could break in a future earthquake. And it is remarkable here that one of these very dangerous areas is right in front of Lima, the capital city. That's the place where I was born. And it's a city of about 10 million people right on the coast. So it's really in the front line for a hazard of earthquakes and big tsunamis. So that's one of the motivations for me to do research, try to do something about it from the perspective of a seismologist and computational mechanics. This takes us to the first question, which is what can rupture dynamics theory tell us about earthquake sizes in this type of segmented fault systems? And the impact of that question is encapsulated in this other question is, can rupture dynamics theory help us improve hazard assessment? And this part of the talk will be based on the paper that we published with Hui Wang. He's a very brilliant postdoc working with me, and he has provided many of the slides that I'm showing today. So that was a JGR paper in 2019, the dynamics of elongated earthquake ruptures. There will be a second question now that relates to rupture speed. These are some examples that you may be familiar with of sources that produce waves. You break a pen and it produces a sound wave. You drop a pebble in a pond, it will produce a gravity water wave. And you can see that this wave has circular fronts, and the source can be simply modeled as a point. You may be familiar with that kind of modeling of earthquakes as a point sources. Now, large earthquakes are more analogous to this following picture. You tear a piece of paper, and that tear propagates and generates a sound as it does. That sound is the analog of earthquake shaking, seismic waves. Another analogy is a ship on water. And you can see here the pattern of water waves that it has produced during its propagation. It's very different from the circular wavefronts that we see from this point source of a pebble in the pond. And some of the analogy here is that we will try to understand, earthquakes, also the ruptures, the sources do propagate fast at speeds that are comparable, sometimes faster than the seismic waves, and they do produce patterns. Some of them will be analogous to this. I could tell you that this other ship that you see in the same picture is also moving, but very slowly. And it wouldn't be difficult for you to trust me on that, because your intuition would tell you that, yeah, if it's moving very slowly, it will barely produce waves. So this intuition is that the faster something moves and the stronger are the waves it radiates. And we'll see that earthquakes also have that property. And that's what makes it important to understand the rupture speed. So here are results from a simulation from an older paper by Eric Dunham and Harshabat. Here's a fault plane in the vertical fault, and they modeled an earthquake that's expanding from the center in both directions, sweeping along the fault. And we are going to look at the ground motion in map view and focus on 1/4 of the space. And we'll consider 3 different scenarios. So here are the 3 map views of ground motion. The first scenario is a rupture that's propagating slower than the S waves. And the other 2 scenarios are ruptures that are propagating faster than S waves. You can see that there is a sharp difference between the wave fields that are produced by these different scenarios. And the most striking observation here is that the faster the rupture and the stronger is the shaking. You see this sharp and very high intensity shaking. And this is actually a Mach front, which is sort of analogous to the front that we saw here in the ship analogy. Okay, what is that? It's also analogous to the sonic boom of a airplane that goes across the sound speed. As that happens, the waves that are emitted or radiated by the source, they pile up on a cone here, which is the Mach cone. And because along this cone, all these waves are arriving at the same time, or they're adding up. So that intensifies the amplitude of the shaking along the Mach cone. So two takeaways from this is the faster an earthquake rupture speed is, and the more damaging, potentially damaging the earthquake can be. And second, earthquakes that run faster than the shear wave speed, these are the so-called super shear earthquakes, are particularly damaging, potentially. So this is why we're interested in studying rupture speeds. Now, what do we know from 2D dynamic rupture theory? So this is a classical theory about the admissible rupture speeds in earthquakes. One case is a pure deep sleep earthquake. We call that also mode 3 in fracture dynamics. And this axis is the speed, rupture speed. And there are basically two domains, below the S wave and above the S wave. Below S wave, well, any earthquake can propagate at those speeds, a deep sleep earthquake, but not above the S wave speed. This is forbidden. We'll see later. What happens here is that the energetically forbidden. What happens in the opposite situation of a strike slip earthquake? We call this mode 2 in fracture mechanics. This situation is a bit more complicated because there's more than one wave speed that is relevant. There's the S wave, there is the P wave, there's also the Rayleigh wave, which is often about 90% of the S wave. And we also have a speed called so-called Eshelby speed, which is the square root of 2 times the S wave. All right, so earthquakes can propagate at speeds that are below the Rayleigh wave speed. And this is what we observe the most often in nature. Rarely, but it does happen, earthquakes do propagate also at super shear speeds. Those are defined as speeds that are larger than S waves. But in the 2D theory, there's a range here indicated in yellow that is unstable. Part of this range is really forbidden energetically, and the other one is unstable in the sense that a rupture that is trying to propagate at a steady speed within that range, if it is slightly perturbed by for example, some heterogeneity of the fault, it will quickly change speed into either the very fast range or the slow range. So this is what we call the unstable range, and we wouldn't expect, based on this 2D theory, to have stable ruptures in those ranges. However, we do see that in some earthquakes, and this is the example of the 2018 magnitude 7.5 earthquakes in Palu, Indonesia. It's a strike slip earthquake that unfortunately produced a tsunami in the Palu Bay. And from our analysis of this earthquake, we do a kind of analysis that's called back projection, is that we use seismic networks that are far away from Indonesia as antennas, and we track how the rupture propagates with those antennas. And the colored dots or circles in this movie here show you the progression of the spots where the high frequency radiation was generated from the fault. So that's moving south. And we can plot it more synthetically. Here is a time on the horizontal axis and distance along strike on the vertical axis, plotting again those high frequency radiators. And the slope of the envelope of these observations here provide you an estimate of the rupture speed, and it's about 4.1 kilometers per second. So what we found about this earthquake is that it is a super shear earthquake. That's 4.1. It's typical S-wave speed here would be closer to 3.5 or so. It is actually the most finely observed super shear earthquake to date. And surprisingly, this speed here, it's not only this super shear, but it's below the Eshelby speed. So it's within this yellow range here that was predicted by 2D theory to be unstable. So that's a puzzle. How come this earthquake managed to propagate at that unstable speed? We can collect observations or inferences of rupture speed from many other earthquakes, and this is what we did in this figure. We are plotting here the rupture speed of many earthquakes as a function of the rake angle. The rake angle is the angle of obliquity of a slip. So a rake angle of 0 means a pure strike-slip fault, and a rake angle of 90 degrees means a rupture, a pure deep slip faulting. And anything in between can occur in nature, and that's oblique slip. Okay, what we see here are for the strike slip, no, for the deep slip earthquakes at the top, near the top, all of them are below S wave speed. And that's what we expected from theory for the deep slip events. For the strike slip events, we do see really at the bottom of the figure, there's some of them are super shear, most of them are sub-Rayleigh. And we see these few earthquakes here that, once again, propagate at speeds within this unstable range. So the Palu earthquake is perhaps not the only example of this. It is rare, just a few points here among the about 100 earthquakes in this plot, but it does occur. So we need to understand it. It does occur, and it's a puzzle because it contradicts the 2D theory, which was the prevailing theory at the time of a couple of years ago. So the question number 2 here is, what can 3D rupture dynamics theory tell us about the rupture speed of large earthquakes? And I'm just trying to address the puzzle of why do some earthquakes propagate at unexpected speeds. And this part of the presentation is based on another paper with Hui Wang, published in Nature Geoscience last year, Continuum of Earthquake Rupture Speeds Enabled by Oblique Slip. The key ingredient of the models that we have developed, and the reason I say we focus on large earthquakes is we're actually focusing on elongated ruptures. The largest earthquakes on Earth, the ruptures saturate the seismogenic depth. Like faults are not seismogenic, that it cannot generate earthquakes, ruptures down to depths, below, let's say, 20, 30 kilometers or 15 kilometers in strike-slip faults, a bit deeper in subduction zones. And this is mostly due to the increase in temperature with depth. So that changes the behavior of rocks from brittle to ductile. So ruptures are confined in the shallowest part of the fault, and once they start to grow bigger, they cannot keep growing deeper, so they have to grow laterally, and that's why they develop large aspect ratios, which means large length to width ratio. And here's a compilation of length to width aspect ratios from earthquakes as a function of their magnitude. You can see here that the largest ones do have the largest aspect ratios out there. But even earthquakes that are, magnitude 6-ish, like the Parkfield earthquake, manage to produce very elongated ruptures. Even these earthquakes seem to be very confined in depth. And we've seen recently an earthquake in France, the Le Teil earthquake, a magnitude 5-ish, which also had a significantly large aspect ratio, especially for its magnitude. So we would plot here. So this happens. Why does it happen? It not only happens for very large earthquakes, right? The earthquakes that go from the bottom of the seismogenic zone to the surface of the Earth. Here's a sketch of a strike-slip fault that is driven in the long term by creep in the deeper parts of a fault. So as this creep occurs, it produces a concentration of stress at the bottom of the locked part of a fault. And that concentration of stress will favor the initiation of earthquakes at the bottom of the seismogenic zone. But sometimes earthquakes initiate, but the whole fault is not ready to break, and only part of the depth range of the fault breaks. And here's an example from a simulation of earthquake cycles in a long fault like this. The blue part of a fault is the part that has been creeping, and the black part of a fault is the locked part. And at the boundary between creep and locked areas, here an earthquake happened in this simulation. And it started near the boundary, but it couldn't propagate upwards all the way through. But it was able to propagate sideways. So it remained confined in depth, and it developed a large aspect ratio. So these things happen very naturally in the earthquake cycle simulations. And it is one interpretation of the earthquake that happened not too far from you in Gorkha in Nepal in 2015. Here's a map view of the source here. So these are contours of sleep. And the surface trace of a fault is here. So it's deeping towards the north, right? This earthquake, if we look at this in a sketch here in 3D, the earthquake remained confined here in the deeper part of the locked zone. It didn't manage to propagate all the way up to the surface. Fortunately, that would have been even more damaging for Kathmandu. But in the future, this shallower part of a fault could break. Anyway, my point here is that this is a good example of an earthquake that's remained confined in depth and thus developed a rather elongated rupture shape. So why is this a big deal? Here's an example of a dynamic simulation of a long rupture. And then you play it again so that you see what happens at the beginning. It starts as a circular rupture, and then it's just a strip of sleep that migrates along the fault. The colors here indicate the velocity of sleep. So that's the velocity at which the two sides of the rock across the fault slide past each other. So here are two snapshots of that. At the beginning, we have a circular rupture, and then we have what we call sleep pulses, that the rupture evolves into sleep pulses. Now, for circular ruptures, there is a good amount of theory out there. And this was well established by the end of the 90s. And there's this very comprehensive book on dynamic fracture mechanics by Friend, published in '89. The basic concept behind our understanding of fracture mechanics is energy, an energy balance. So during rupture, the energy that has been stored before the earthquake by elastic deformation, so that's a potential energy. During the sudden rupture, this energy gets transformed into two different things. One is earthquake waves, seismic waves, so that's radiated energy. And another part of that energy flows towards the propagating rupture tip, towards the rupture front. And there it is transformed, or it's dissipated into what we call fracture energy. So those are all the friction and fracturing processes that happen close to the rupture front. So for circular ruptures, it is well established mathematically, mechanically, that this energy balance can be written in the following way. So we have this fracture energy, which it's the energy that can be dissipated by the fault, and is equated to the energy release rate per unit of crack advance. And that's what we have on the right-hand side here. And it involves a few things, a few parameters of the problem. G is a known function of rupture speed. V is the rupture speed. R is the radius of the circular rupture. Delta tau is the stress drop, and mu here is the shear modulus. Some of these quantities are known, so the shear modulus, yes, we can have good constraints on that from rocks. The stress drop, well, we can estimate that from seismological observations. And the rupture speed, well, it's a variable of the problem. It's the rupture is growing, so this is changing with time, and the speed also. Now, in this equation, the unknowns are the rupture speed and the rupture position as a function of time. The rupture speed is the derivative of the rupture position. So this provides a differential equation that one can solve to compute the evolution of the rupture position. So that's why we call this a crack tip equation of motion. So by the 90s, this was the available 2D theory. But there's a research gap, and an open question is that theory applies well to circular ruptures, but what happens once the rupture becomes long and becomes a pulse? There was no theory available for that, and that's what we set up to develop in our work with Hui Wang. We do know from dimensional analysis and from other arguments that we expect these two situations to be radically different from the point of view of energy scaling. The energy release rate for a circular rupture scales with the growing rupture radius, whereas for a long rupture, the energy release rate scales with the rupture width. It doesn't scale with the rupture length, so it doesn't keep growing. So that is a major difference between these two problems, which prompted us to develop a specific theory for this situation. So in the rest of the talk, I'll try to highlight a few things that we did during our research. It's a combination of all these things. It's iterations between many of these things. One is, being aware of the past literature and what has been done, not only in earthquake dynamics, but in fracture mechanics in general. So that's literature search and being up to date with that literature. That is one of our sources of inspiration, as you could see. The second tool we have is analytical work, so that's pen and paper work. We can do that once we have simplified the problem in a way that is mathematically tractable. When it's not, when we do large 3D dynamic rupture simulations, we have to use big computers. So high performance computing is another one of our tools. Sometimes you will see we are able to, once we have understood some of the problem, we're able to simplify it, simplify the equations in a way that that makes the problem more tractable, not only analytically, but also computationally. And maybe those computations can fit on a smaller computer, and we can do more of them and study more thoroughly on the problem. And then circling back to the observations, the seismological observations, and so on. That's another source of inspiration, but also a source of validation for our theoretical and computational developments. So inspiration came from an old paper by Marder. He's not a seismologist, so this is a paper in fracture mechanics. He was looking at the problem of how a crack propagates in a strip, an elastic strip. That's a medium that has a finite width. So think of it as having a boundary condition here at the top and bottom that is a prescribed displacement. And this crack is opening and propagating to the right. Yes. In this situation, he found that the steady state rupture, the steady state energy of the rupture was, as I showed in the previous slide, was controlled by the width of the problem, not by the length of the rupture. Sorry, there's a typo here. The square should be on the stress drop, not on the width. It's proportional to width. Okay, he also worked on the non-steady rupture problem. A steady state means that the speed is constant. And non-steady, the speed is variable. So what happens when the speed can change? And he found that an equation of motion of this form, remarkably, it's an equation of motion that involves the derivative of the rupture speed as the rupture acceleration. This is the main difference with the 2D theory. We can rewrite this in a different form that makes an analogy to the classical equation of force equals mass times acceleration. So the forcing term here is going to be the ratio between the fracture energy that's the resistance of the fault, and the potential energy, this G0 term here. That's the elastic energy provided by, for example, the tectonic loading over the long term. So that's all the forces on the left-hand side. The mass, this is a known function. I'll show you the mathematical form of that later. That depends on rupture speed, and then we have rupture acceleration. Okay. So what did we do? We set up to show that in 3D, a similar equation was sufficient to explain to a large extent the behavior of very long ruptures. So we ran a systematic set of very long dynamic rupture simulations using a high-performance computing cluster. And here are some of his numerical results. So here are the rupture speed on the vertical axis as a function of distance in examples where the energy, the potential energy is larger than the dissipated energy, and in the opposite situation too. In the former, because the available energy exceeds the dissipated energy, the rupture can accelerate, so the speed goes up. And the opposite happens in the opposite situation. The speed goes down, rupture decelerates, and eventually stops. In bingo, he was able to fit this numerical results with an equation of the same form that Marder had proposed for a different problem. So we have here, again, this mass, acceleration, and force on the left. I can show you a little bit more of the things that we did after this. We simplified the problem. So starting from the 3D elastic wave equations, we can do some approximations in order to turn the 3D problem into a reduced dimensionality problem that we call 2.5D problem. Basically, if we're looking here at the fault and we do a special weighted average of quantities across depth, we can transform these equations into a set of 2D equations that now only depend on two variables in map view, so the two horizontal positions here, and that we have averaged out the depth behavior. So that's a 2.5D. The interest of this is that it has the same computational cost as a 2D simulation, so it's much cheaper than a 3D simulation. But moreover, not only you can run it on a laptop, but it's also amenable for analytical solutions, pen and paper. So we were able to show that for this 2.5D problem, derive the mathematical expression for that effective mass of a rupture of an elongated fault. So I'll skip the details of these. You can find them in our 2019 JGR paper. It's so the take-home message of this part is that after overcoming one crucial limitation of the classical 2D theory, namely the finite depth of a rupture, we're able to develop this new 3D equation of motion, and that can be used then to predict the evolution of the rupture speed. So because we can predict the history of the rupture speed, if we know the left-hand side, right? What are the implications of this on earthquake size? In particular, we can make some predictions of when the rupture will stop, right? It's rupture arrest. So it's interesting that this is something that's very different between the 2D and the 3D theories. In the 2D theory, there's the rupture acceleration is not involved in the crack tip equation of motion, but it is in the 3D theory and in the 2.5D theory. This introduces inertia. And what is the implication of inertia? If you have a rupture that's propagating and entering into a barrier, which means an area where the fracture energy is larger, there's more resistance on the fault. Well, the fault will tend to stop or slow down. And this happens in a very different way in 2D and 3D. In 2D, when the rupture hits a barrier, it stops, boom, immediately. But in the 3D theory, it stops, it manages to penetrate into the barrier to some distance. So it stops progressively. And this is because in 3D, the rupture does have inertia. That's this term here on the right. Now we can manipulate the equations to come up with some simple recipes for the prediction of rupture arrest. So here, this would be a simulation where we're plotting here the rupture speed as a function of the distance of rupture propagation. So this rupture accelerates, and then because it finds perhaps some area of larger fracture energy, more resistance, it slows down and stops. So from the equation of motion, we can integrate it. And we see appearing here after integration something analogous to a potential energy change in the left-hand side and something analogous to a kinetic energy change on the right-hand side. And the kinetic energy, well, it's 0 at the beginning and 0 after the rupture. So if we can integrate this equation from before the earthquake to after the earthquake, this kinetic energy should be 0. Kinetic energy change. So that equation, brings us to this equation here at the bottom, in which we can define now a rupture potential, which is this quantity here in the integral. So what can we do with that rupture potential? So let's call it phi. It will have, because of the inertial type of the crack tip equation of motion, it will play a similar role as the gravity potential plays in the problem of coming up where asking how will a train move in the roller coaster, right? So the roller coaster here is made of the heterogeneities along the fault of this rupture potential, which are controlled by the heterogeneities of fracture energy and the heterogeneities of the potential energy. The potential energy mainly depends on how much the stress has been accumulated on the fault. So that's the stress drop squared. So let's imagine that we have this landscape of potential along the fault. And so that's the integrand, and this is the integral of that is the potential. And if an earthquake starts at this position, it will be able to propagate up to, it will stop at the point where the potential is the same as the potential at which it started. So that is the practical way of using this potential to predict the rupture arrest position if you know the landscape of fracture energy and potential energy. If the earthquake doesn't happen yet, but happens later, let's say 50 years later, and more energy has accumulated, so this G0 term, the potential energy has changed, the earthquake potential might change too. And now if an earthquake nucleates here, it will manage to propagate a little further right? Because the level has gone up. So this is something that seems to be quite useful if we can estimate these quantities here. So how do we do that? The potential energy, well, as it depends, two things here are constant, do not change with time, which are the rupture width and the shear modulus of the material. But what is changing with time is the potential stress drop. So this is as the fault builds up stress, the potential stress drop becomes larger. So that's what we know about this term here. And what do we know about fracture energy? Well, this can be somewhat constrained by seismological observations. And there's a very nice paper by Rob Vieska and Garagash showing one example of how can one use seismic observations and the theory of thermal weakening to explain how the fracture energy might depend by scale with a sleep. So when we have these two portions of the earthquake potential, and if we take this sleep as being the sleep deficit that has been accumulated and that we can estimate from geodetic observations, so those are the coupling maps, one I showed one earlier, we can use these potentials to make some statements about what is the potential size of an earthquake currently or in the future, because we know what is the rate of accumulation of this sleep deficit. And so early on in the earthquake cycle, that means right after a large earthquake, this sleep deficit is small, and only small earthquakes can break. So this is time on the horizontal axis and latitude along the subduction fault in the vertical axis. Here's a situation where only a small earthquake breaks if it nucleates here. If it nucleates a little in this other position, it can break the whole segment. So this helps us make some relations between hypocenter location and potential size of earthquakes, and also say something about time-dependent hazard. So in summary for this first question, what can rupture dynamics theory tell us about earthquake sizes? We have come up with this theoretical framework that can help contribute to physics-based hazard assessment. Now let's go to question number 2. What does the theory tell us about the earthquake rupture speeds? And repeat again, the puzzle was that there are some earthquakes that propagate at this within this range of rupture speeds that seems to be, that in 2D theory would be inadmissible. Now, we plotted this as a function of the rake angle, just the obliquity of a slip, and that seemed to be a parameter that's important. So in our work, we did study that in detail, how the obliqueness of slip changes the energy balance and the rupture behavior and the rupture speed. The energy balance actually for what we call a mixed mode rupture, that's a mode that's a rupture with oblique slip, is the sum of the contributions from the two components, the deep slip component and the strike slip component. When this at rupture speeds that are larger than S-wave speeds, actually, no, it's not the strike slip, the deep slip component of the energy is negative. So that makes it inadmissible in 2D. But in 3D, the sum of these two contributions is not negative, it is positive. So it is admissible in 3D. So it is actually this combination that makes it admissible in 3D. And we did run simulations with different rake angles, and we do see how the rupture speed, as the rupture propagates as a function of distance, stabilizes at different speeds, and those speeds depend on the rake angle. And remarkably, there are speeds here that are achieved that are very steady, but they lie within this inadmissible range of the 2D theory. And this only happens in 3D. intuitively, what is the idea here? Rephrase it in different terms, right? For a pure strike sleep, we have the possibility of very high ruptures, the super shear ruptures. For pure deep sleep, we don't. Ruptures can only be sub shear, so relatively slow. So we have the fast runner and the slow runner. Now, if these two runners team up and they run together and tie to each other, well, the faster runner will pull the slower runner a bit faster, and so and vice versa. So on average, or the two of them in tandem, they will reach an intermediate speed, and they can reach the whole range of intermediate speeds between pure strike sleep and pure deep sleep. So we obtain from that theory the following speed diagram. It shows as a function of the ratio of dissipated to potential energy on the horizontal axis, and as a function of the rake, the oblique angle of sleep, all the expected rupture speeds for steady ruptures. And we have here in green earthquakes that cannot propagate. They have too low energy to start with. Then we have the sub-shear, those relatively slow or regular earthquakes, if you wish. We have the forbidden speed and the unstable speed in yellow and orange. They don't exist for pure strike sleep, but this exists in the middle. And the super shear ruptures in red. And we can compare this to the observations, and actually these black curves that you see plotted here in the background are actually coming from the theory and the simulations, and there is some consistency between the theory and these observations. So we circle back to a better understanding of these previously unexpected rupture speeds. So this brings me to the conclusions. So we have developed this new 3D theory of rupture dynamics, and which is special for very long ruptures. That means ruptures that are longer than they are deep or wide. And we account for the finite rupture width and for the obliqueness of sleep. And this helps us gain insights on rupture arrest, on rupture speed, and it moves us towards physics-based, or gives a tool, a framework for physics-based hazard assessment. There's still a long way to go to convert this into a practical hazard assessment tool, right? But I think we've made a good breakthrough here. Among the perspectives are the validation of these findings in laboratory experiments. We can design laboratory experiments where we control and where we limit the rupture width, and also in observations, right? Unfortunately, there's the observations of real earthquakes across multiple cycles and multiple segments are scarce, right? We haven't observed yet a same fault operate across multiple earthquake cycles, because the earthquake cycles take centuries. But there's another phenomenon called slow sleep events, which are they are slower, but Hui Wen is working on this, and he's finding that they can be described by some of the theory that we showed today. And the advantage of a slow sleep events is that the recurrence time is just 6 or 12 months. So we have already observed in the past 20 years more than 20 slow sleep events in the same fault in some areas. So there's a big opportunity there to validate with observations this theory. All right, so I'll finish there, and I will encourage you to go and read these two recent papers, and then perhaps come back to these slides and help you understanding some of these recent advances. Thank you for your attention.